Hello everybody, this is Dr. Christopher White and welcome back for part 3 of Cenozoic Earth history focusing on the Quaternary. So before we go any further, let's just get the code word out of the way. The code word for this presentation is Greenland. I repeat, Greenland. That's Greenland. That's Greenland. Please make sure you write that down, put it somewhere safe, because you'll need it for the code word quiz. So now we need to think about what actually caused the Pleistocene glaciation. Now, as discussed, the most basic reason for the formation of glaciers is that you get more snowfalls in colder months than melts in the warm months, so you have a net build-up of snow and ice. But the more important questions are, why do these conditions occur, and why have they actually occurred so rarely in geologic time? So when you think about it, we don't actually have many examples of these large-scale glaciations. So we know we have large glaciations at the end of the Proterozoic. We know we also have large glaciations occurring during the Carboniferous, and we know we have these large-scale glaciation occurring as part of the last ice age. But in between those events, there are huge amounts of geologic time where we don't have these glacial events. And so this is showing us that the conditions that lead to the formation of large glaciers, large glacial events, are obviously relatively rare. So the problem is that the climatic change responsible for glaciation and the cyclical nature of glacial interglacial events and the additional complication of short-term events all operate on different timescales, and so we have lots and lots of different processes occurring. They're all operating on different wavelengths essentially. And so this means that the chances of you getting all these different factors converging at the same time are relatively low. And so this makes it less likely you're going to get these glacial events. So the question then becomes is, well, what are the conditions we're looking for in order to encourage the formation of large amounts of glacial ice? Now, the few periods of mass glaciation that we've recognized are separated by extensive periods of warmer climates. Now, this can be explained by changes in ocean and air circulation patterns and levels of volcanic activity. So that's obviously going to have a serious effect on greenhouse gases, and thereby it's going to cause an increased or decreased greenhouse effect. Typically, when we have lots of volcanic activity, more carbon dioxide enters the atmosphere and the greenhouse effect becomes stronger. And this is obviously going to inhibit the formation of large amounts of glacial ice. Now, furthermore, we know that plate tectonics may also bring continents into latitudes where glaciation is possible from regions where they may not have been capable of forming glaciers. And the reverse can occur as well. So if you go and distribute all of your continents along the equator, well, that's obviously going to mean that the chances of you having an ice age are reduced because it's more difficult to form glacial ice in tropical regions. In contrast, if you were to push all the continents towards the poles, well, that would obviously displace warm seawater with cold continental crust, and so that would encourage the formation of ice sheets, both because the continental crust has moved into areas which are essentially, well, because the continental crust will encourage the nucleation of ice, and it's being pushed into areas which are naturally more cold. And so on the very first level, what we are looking for is a decreased greenhouse effect, because that's going to help to drive down global temperatures, and we want continental crust to be located near or at the poles. So those are the first couple of conditions which we want. Now, greenhouse gas levels are often considered to be a possible cause for glaciations. You know, it makes a reasonable amount of sense. When greenhouse gas levels are low, the greenhouse effect is going to be weaker and the global climate will therefore be cooler. And, you know, given the right conditions, this could lead to the onset of a glacial event. Now, we know that carbon dioxide levels decreased after the Mesozoic, and this is either due to a decrease in volcanic activity, because for a larger period of time during the Mesozoic we have the Deccan Trap flood basalt eruptions of India, and these huge volcanic eruptions would have pumped out absolutely vast quantities of carbon dioxide, and so that would have helped to increase the greenhouse effect. Now, as we transition from the Mesozoic into the Cenozoic, the Deccan Trap eruptions stop. At the same time, we also have India beginning to interact with Asia, forming the Himalayas, and this occurs about 50 or so million years ago. And what we see occurring when the Himalayas begin to form is we obviously see an increase in the rate of erosion. And as part of the erosional process, one of the chemical reactions that can take place is you can have carbon dioxide from the atmosphere reacting with water and calcium-bearing minerals, and that can lead to the formation of calcium carbonate. And so the formation of a large mountain range like the Himalayas and the high rates of erosion which are associated with those large mountain ranges can also help to strip carbon dioxide from the atmosphere. So both of these factors combined would have been sufficient to have caused a decrease in global carbon dioxide levels and therefore a decrease in the greenhouse effect. So that would make a lot of sense as a possible cause for the onset of the last ice age. The problem is that there's no hard data to actually support that idea. So it's not like we see the carbon dioxide levels dropping and then straight away, bang, we have an ice age starting. It doesn't work that way. We don't see that in the rock record, and so that would suggest that maybe the greenhouse gas levels are playing a part, but it's clearly not the only cause. There must be other factors operating which are also having an effect. So trying to explain intermediate range climate changes, so those that last a few thousand years to a few 100,000 years, is even more difficult. So we can explain the big changes, we can explain them based on things like changes in ocean circulation and changes in atmospheric greenhouse gas levels. But on the smaller timescale, trying to explain, relatively short-lived changes in climate on both local and global scales is even more complicated. And so, as you can see, it's a very difficult problem because there's just so many variables. Now, there is one theory that, to some degree, does help to explain the onset of glaciations. So, this is called Mendelovitch Theory. So it was proposed in 1920 by a Serbian astronomer, and his proposition was that minor irregularities in the Earth's rotation and orbit around the Sun will impact the amount of solar radiation that the Earth or certain portions of the Earth will receive on a yearly basis. And so what he's saying is if you manage to reduce the amount of solar radiation an area of the Earth's surface is receiving, that's going to result in a cooler climate. Now, Mendelovitch attributed the onset of the Pleistocene Ice Age to three variables in the Earth's orbit: the Earth's orbital eccentricity, its axial tilt, and its axial precession. Okay, so let's start thinking about orbital eccentricity. Now, this one works on a cycle of about 100,000 years. So the Earth's orbit around the Sun is not circular, it's actually elliptical. And this means that the distance between the Earth and the Sun will change as it orbits around. Now, over time, the degree of eccentricity will change. So sometimes the Earth's orbit is more circular and sometimes it's more elliptical, and these changes will happen on a 100,000 year timescale. Now, the Earth's orbit has two important points: the aphelion, and this is when the Earth is at its maximum distance from the Sun. So that's its furthest point from the Sun during its orbit. And then we have the perihelion. This is when the Earth is at its closest point to the Sun as it orbits around. Typically, the greater the distance, the less solar radiation will be received by the Earth, and the colder the climate will be. So if the aphelion falls in the winter months, so that's the greatest distance between the Earth and the Sun, the Earth will obviously be receiving less solar radiation, and so this would result in a cold winter. In contrast, if the aphelion falls in the summer months, you will end up getting a cool summer because you'll be receiving less solar radiation. So you can see how this would begin to have an effect. Now, when the Earth's orbit is near circular, the northern and southern hemispheres have similar contrast between the seasons, and this will change as the orbit becomes more elliptical. So if we look over here at this diagram, you can see we have two orbits: a solid white line which represents a circular orbit and a dashed white line which represents an elliptical orbit. So let's just think about how the seasons would vary between these two different orbits. So let's just say over here, this represents the northern hemisphere summer, and so over here we would have the southern hemisphere summer. Now, because the distance is the same on both sides, it means the summer conditions for the northern and southern hemisphere would be the same, and that would also go for the winter conditions. So you would have very similar conditions between both the north and the southern hemisphere. So the northern hemisphere summer would be very similar to the southern hemisphere summer, and the southern hemisphere winter would be very similar to the northern hemisphere winter. Now, as the orbit becomes more elliptical, this situation changes. So let's just say, for instance, we have a situation where this represents the northern hemisphere summer. Well, obviously we're a very long way from the sun at this point. So in the northern hemisphere, we're going to have a very cool summer, and in the southern hemisphere, we're going to have a very cool winter. When the Earth is on the other side, we would have a very, very warm winter for the northern hemisphere because we're so close to the sun, and we would have a very warm summer in the southern hemisphere. So the difference between the seasons between the northern and southern hemisphere would be a lot more pronounced. Now, typically what this means is the greater the difference between the winter and the summer, typically the more snow will accumulate in the colder winters, and the more snow will be lost in the warmer summers. Now, under normal conditions, the ice and snow will accumulate in the winter and it melts in the summer. That's not a huge surprise. Now, in order for a glacier to expand, we actually want to focus on minimalizing the melting. So what we really want are cool summers. So one of the things that people don't realize until you've lived in a very, very cold area like Canada, for instance, is that when the weather gets very, very cold, it actually inhibits the capacity of snow to form. And so very, very, very cold winters will actually result in lower snowfalls. Typically, you want your winter to be a little bit towards the warmer end, and this will help to encourage large amounts of snow to form. Now, obviously, what we don't want is a nice warm summer. So typically what we want is a relatively cool summer and a slightly warmish winter. And both of those factors combined will result in heavier snowfall in the winter and less snow melting in the summer. Now, obviously, this means that when we have a situation where we have a very eccentric orbit, well, yes, elliptical orbit, sorry, we could end up with a very, very cool summer, which would be great, but at the same time, that would also mean we would end up with a very, very warm winter. So let's just think about this the other way. So here's our situation. So let's say this is the Earth again, and in this instance we're going to pretend that here we have a situation where we are in the summer months for the northern hemisphere. And so the distance between the sun and the Earth is obviously at its greatest. Summer months, we're going to get a nice cool summer. Now that's good for glaciers. However, when we're over here, we can see the Earth is going to be at its closest to the sun. So this would be the northern hemisphere winter. So in this situation, we might end up with a very, very warm winter, and a very warm winter is obviously going to stop snow deposition. It's going to mean that any snow that gets deposited will melt, and so that's going to inhibit glacial formation. Let's think about this the other way then. Let's pretend that this is the northern hemisphere winter over here. Well, in this case, we're going to have a very, very cold northern hemisphere winter, and that might actually inhibit snow deposition. When we come over to the other side, over here, we're going to have a very, very warm summer, and obviously that's going to cause lots and lots of melting. So you can actually see that very elliptical orbits are actually bad for glaciations. What you want is an orbit that's kind of somewhere in between a circular orbit and the most extreme elliptical orbit, because that's going to offer you a good contrast between the seasons, but at the same time the seasons aren't going to be too extreme. Now, this obviously means that the Earth will only rarely achieve the kind of orbit required to produce the conditions we want for a large-scale glaciation. So the 100,000 year cycle length for eccentricity matches very, very nicely with the 20 interglacial periods which we have from the from the Pleistocene. So obviously we have 20 interglacial periods. We have a cycle of 100,000 years. That's going to equate to approximately 2 million years of time, and we know the last ice age was about 2.6 million years. So this equates absolutely wonderfully. So essentially what it comes down to is what we really want is an orbit that's going to encourage relatively cool but not excessively cold winters and cooler summers. That's what we really want. So our next variable is axial tilt, and this operates on a 41,000 year cycle. So the axial tilt is the difference in angle between the Earth's rotation of axis of rotation and the geographic north and south poles. So the geographic north and south poles are simply put there by map makers, and those are essentially the poles that stick out at the top and the bottom of the Earth. In reality, the Earth doesn't actually rotate around the geographic poles, it rotates along the axis of rotation, and the axis of rotation is actually offset from the geographic north and south poles, and the axis of rotation can be anywhere between 22.1 and 24.5 degrees off the geographic north pole. At the moment our current tilt is about 23.5. Now the steeper the angle, the more solar radiation a pole will receive. And this is because the steeper the angle, the more of the pole will be exposed to the sun. And so the more solar radiation the area receives, the warmer the climate will be. So if we have an axial tilt of 24.5 degrees and the northern hemisphere is facing the sun during the winter, well, this would mean we would have a very warm winter. Now, if the axial tilt is 22.1 degrees, so that the lowest angle, the pole will receive less solar radiation in the winter, and this would actually result in a cold winter. So you can see pretty quickly what we want is we want our axial tilt to be as low as possible. 22.1 is the number we're really looking for. So a low axial tilt is advantageous for ice sheet growth as it limits the occurrence of warmer summers and winters. So typically the lower the angle, the cooler the cooler the summers and winters will be. So the effect of the axial tilt is actually quite small. However, the combined effect of the axial tilt and the next variable can actually lead to a change in solar radiation levels of up to 15%. So when we combine axial tilt and axial precession together, it can actually reduce the amount of sunlight received by a pole by up to 15%. And obviously the less sunlight we have, the less solar radiation we have hitting the pole, the colder that environment will be, and therefore the more likely we are to start a large-scale glaciation. So our final variable is axial precession. This operates on a 25,000 year cycle. Now as the Earth rotates, you can see, if we look at this diagram, that the axial plane doesn't actually stay stable. Instead it rotates in a circular motion, and this actually produces a wobble in the Earth's rotation. Now what this means is the tilt of the Earth will change over time. So you can see in this picture the axis of rotation is orientated northwest southeast. However, given enough time, the axial plane will actually come over here and the axis would then be situated in a northeast southwest orientation. So you can see over time the angle of the rotation of axis will be changing. Now, if we look at this diagram down here, this is actually going to demonstrate what changes this will produce. So if we look here, you can see we have 4 scenarios where we have the Earth orbiting around the Sun. Obviously the Sun is the yellow dot in the middle, and the Earth is represented by these blue circles. And the red line here is representing the Earth's axis of rotation. So what we can see here is that we are looking at the northern hemisphere. And so we can see in this instance, we can see the axis of rotation is pointing the northern hemisphere away from the sun. So this means we're going to get colder conditions. So this is going to be either the fall or, as we are over here, the winter. So as the pole is facing, axis of rotation is facing away from the sun, that means less solar radiation from the northern hemisphere, and that's going to lead to colder conditions. Now, during the spring months and the summer months, we can see the axis of rotation is going to be pointing the northern hemisphere towards the sun, and this is going to result in warmer conditions, so not really a huge surprise there. Now, what you're going to notice, though, is that as we look through Earth history, we can see that the position of the axis of rotation has been changing. So this goes back from about 12,000 years ago, the end of the last ice age, through to the present day. So at the end of the last ice age, we can see that at this point here, where in the modern day we have cooler winterish conditions, so fall and winter conditions, 12,000 years ago we would have had more spring-like conditions. It would have been warmer. And so you can see that conditions where we are in the spring and summer in the modern system would actually have been autumn and winter about 12,000 years ago. So you can see how this wobble and its effect on the Earth's axis of rotation is going to have a quite substantial, is going to cause quite substantial changes in the amount of solar radiation received by a pole. Now, when you combine that with the change in axial tilt, if you can get a 22.1 degree axial tilt, and combine it with a situation where we have the Earth's axis of rotation facing away from the sun in the spring and summer, well, that would obviously lead to quite cold springs and summers, and that would be quite good for glacial formation. Now, at present, the axial tilt points the southern hemisphere towards the sun at the Earth's perihelion. So essentially that means the southern hemisphere has nice warm summers. Now, in about 13,000 years, axial precession is going to cause the northern hemisphere to face the sun at the Earth's closest point, and so this means in about 13,000 years' time, we are going to be having very, very warm winters in the northern hemisphere. So the axial precession causes the timing, length and average temperatures of the seasons to change, and one complete cycle will take about 25,000 years. So these three factors combined are obviously going to result in changes in the amount of solar radiation received by certain parts of the Earth's surface. Now, the continuous variation in these factors causes the amount of solar radiation received at different latitudes, particularly the higher latitudes, so towards the poles, to change slightly through time. Interestingly though, the total amount of energy received by the Earth doesn't change very much. What we're actually talking about is changing the distribution of the solar energy. So what we're trying to do is we're trying to change how much solar energy the northern or southern hemisphere receives at certain points of the year. Now, obviously, this can cause very complex climatic variations, possibly producing or triggering a mechanism for glaciation. So the problem is that yes, we have these three variables, and yes, they're going to contribute, but on top of that, we are also going to have the complicating factors of things like greenhouse gases. We're going to have, the effect of global warming related to human beings. We may have other variables which will also affect global temperatures, something like large-scale volcanic eruptions throwing lots of dust and ash into the high atmosphere, which could cause the global climate to cool down. So the Mendelovitch cycles on their own aren't truly going to be sufficient to induce a large-scale glaciation. However, if we wanted to encourage or at least improve our chances of producing a northern hemisphere glaciation, for instance, what we would really want would be the aphelion to fall in the summer month, which is going to give us a cool summer, so we're going to lose less snow and ice through melting. We want the axial tilt to be low, typically about 22.1 degrees, and this means the northern pole, or the North Pole, will receive less solar radiation, and as such it will be cooler, which will once again encourage ice growth. We also don't want the orbit to be excessively elliptical. We want it to be somewhere between a circular orbit and the maximum elliptical orbit. And this means that we get winters which will be not too hot and not too cold, and we'll get summers that won't be excessively hot. And this will encourage the development of snow and ice during the winter period, and it will minimize the amount of melting we get during the summer period. And this will lead to a net expansion in the amount of glacial ice. Now, the thing we need to remember, as I just said though, is we have to bear in mind that additional factors, so things like volcanic eruptions, or maybe the Earth passing through an interstellar dust cloud, can also play a part. So it's not just the Mendelovitch cycles alone which are going to control whether we get these mass glaciation events. So the final thing we need to think about are short-term climatic events and what effect they're going to have. So on top of the Milankovitch cycles, there are also going to be short-term effects that help to vary global climate and possibly cause or inhibit large-scale glaciations. So a classic example would be something like an explosive volcanic eruption that puts large amounts of dust into the high atmosphere. So in 1990 in the Philippines, a volcano called Mount Pinatubo went and erupted. It was a very, very large eruption. It threw lots and lots of dust into the high atmosphere. And what this dust does when it enters the high atmosphere is it actually reflects solar radiation back into space. And so for 2 years after the Mount Pinatubo eruption, so from 1990 to 1992, we actually saw a noticeable decrease in global temperatures. Now, this was obviously a short-lived event. It only lasted 24 months. In contrast, the carbon dioxide put into the atmosphere by large, long-lasting volcanic events, so something like the Deccan traps or the Siberian traps, can cause global temperatures to increase. But remember, these large-scale eruptions are going to be operating on a very long time scale, so they're not going to be considered short-term events. Now, we can also have events such as the solar system passing through a cloud of interstellar gas. So we always think about our solar system as a relatively stationary thing, but it's not. We're part of a galaxy, and that galaxy is moving, the galaxy is rotating, and so the solar system is constantly moving through space. And occasionally that means the solar system is going to go ploughing through a gas cloud or a dust cloud. And this is obviously going to reduce the amount of solar radiation the Earth receives from the sun, because the dust or the gas is going to scatter a certain amount of that solar radiation. So that's going to mean the conditions will get a little bit cooler. And of course, we can't always overlook the introduction of a new species onto the surface of the Earth that decides what they really need to do is burn a whole load of fossil fuels, putting in tons of carbon dioxide into the atmosphere, helping to rapidly increase the greenhouse effect. Yes, we are considered to be a short-term climatic event. So there you go, aren't we special? So these short-term events are also going to contribute to the chaotic nature of glaciation, and so we just have to bear in mind this helps to explain why we've only had a very limited number of large-scale glacial events, because in order to make them happen you need just the right conditions to all occur at exactly the same time, and that's going to be very, very difficult to achieve. Okay everybody, well thank you for sticking with me. I hope you found the presentation informative, so have a good day and take care.